So it is a real pleasure to be here. I have very many fond memories of trips to Copenhagen and Denmark and Aarhus, and this is a great experience, chance to talk with you today. I've chosen this title. It's not the same as the title that has been circulated, but it's a title that's probably pretty familiar to you because everyone who talks about the Nobel Prize has received this phone call which ends in this ominous phrase, and your life will never be the same again. And for most of us who are lucky enough to have received the Nobel Prize, actually our lives have been pretty good up until that point. So this is kind of quite a warning. And we had this sort of be pretty sober about this when you started thinking, my life will not be the same. No, I refuse, I'm going to be the same. Well, should I, shouldn't I? So that's the introduction for today. And so I want to take this sentence, this phrase, and look at it a little more closely. So, for one thing, it's not the only life-changing event that's ever happened. In fact, we all have many life-changing events, and it's worth thinking about them. I mean, when I was little, my sisters came along a little bit after me, and I had twin sisters, and that's a life-changing event. We get married, and this is what a wedding looked like in the 60s. You see a lot of flowers in the hair and so forth. And then we had children. Here's my daughter, Lindsay, and my son, Jordan. These are all life-changing events. We moved to California. That was a life-changing event. I joined UCSD and teamed up with Clive Granger, who was my colleague for 25 years in San Diego, and this is a nice picture of Clive here. He unfortunately has passed away. Mark Machina is still with us and still in San Diego. But that was also a life-changing event because Clive was a great colleague, and he and I did just a lot of good things together, including working on the co-integration paper, which Lasse was talking about. But we also visited Denmark, and this is, I think this is Gemmel Aarhus when my kids were little, and this is a little trip we took up to the top of Jylland, and I'm sure most of you have seen this. So when I was growing up, I was always very interested in physics. I'm not exactly sure how that started. My father was a chemist, but I really liked physics. And somehow I got myself over to the Swarthmore College Library, which had a physics library. And there were these little dusty books on quantum mechanics by Dirac and Schrödinger and Heisenberg. And I mean, I didn't really understand what they were doing, but I was fascinated by it. And then one of the things that I think was probably pretty important was I spent a lot of time working with my father on science projects. I used to make rockets. Some of them went up. A lot of them exploded. That was pretty exciting. Then we did science projects, and science projects were something I really loved. My senior year, I built something called a Van de Graaff generator, which is a static electricity generator. I used a sewing machine motor and a toilet float. I had an old X-ray tube from a hospital waste bin and made a Geiger counter with some radio parts, and I was just happy as a clam. I was very happy. But then I switched to economics, actually, when I was in graduate school, And my dad was kind of disappointed because he thought physics was really a great career, and actually I did too. But I thought economics had some real advantages because, well, one thing I was worried about in physics is that I could spend my entire life and only 10 people would really know what I was doing. And I thought I wanted to do something that had more broad interest. And economics, being the most mathematical of the social sciences, seemed like a natural direction, and that's what I did. So I explained to him that I would still be building things. And I think I do. That is really kind of what I do in economics. I create statistical methods which help us solve complicated problems of humanity and society, a little bit. And so I feel like it is kind of a natural extension of physics. I think that physics gives you a way of viewing the world as a scientist. There are all these natural phenomena going on, and you build little experiments and you try to see what's going on. In economics, you can't really do little experiments, but you can still think about the economy as being this body that you're trying to study, and we measure different aspects of it. Same way a scientist measures aspects of his experiment, and then you try to infer what's going on inside, and maybe forecast, maybe ask what it would do if something else happened, some counterfactual. So I think we can feel like economics is an experimental science, much as physics is, but it's a different organism that we're studying. So one of the important things in my life was a sabbatical I took in London, where the arch model was something that I discovered. And I was visiting at London School of Economics with a lot of great statisticians, many of whom are longtime friends. And this was a great place for me to do this work. This is the paper that actually was cited for the Nobel Prize. It's the autoregressive conditional heteroscedasticity model, or the arch model. And interestingly, it's a model of the variance of inflation, not the variance of a stock market, which is what I've sort of been doing for a large number of years now, but it's the variance of inflation. So where did this come from? Well, in fact, the arch model was the result of 3 different things that I was thinking about at the same time. And actually, I think it's helpful to be thinking about a lot of different things at the same time. The first was Milton Friedman's Nobel address, which I had recently read. And in case you haven't recently read it, what it is a theory which is that uncertainty about the future, particularly the future level of prices, could actually discourage businesses from investing. And if businesses don't invest, then the economy won't grow as fast. So this was a theory of the business cycle based on uncertainty. And I was trying to figure out how would you test something like that, because we didn't have models which allowed uncertainty to change over time. Uncertainty was measured by something like a variance, and once you had it, that's all there was. So that was the first part of this. The second part was I'd been studying the Kalman filter. It was a way of updating your expectations every time you get a new piece of information, and I figured out that you could update your expectations about variances just like you update your expectations about the mean. And thirdly, Clive had recently shown me his test for a bilinear model, which is a kind of nonlinear model. And I realized that when you took the residuals from ordinary macroeconomic regressions, if you they're not autocorrelated when you take the residuals, but if you square them, they may become autocorrelated. And I hadn't realized that that would be a kind of pervasive observation that you could make about economic data. But once I observed this, I realized that was the evidence that there was an arch effect going on in macroeconomics. And of course, we now know this is we call this the arch test in finance. So taking this idea gives you sort of a suggestion, which I think is useful for what a research project ought to look like. I often teach this to my students who are looking for dissertation topics. I think research has three legs: good theory, or maybe just a very good question, good econometrics or methodology, and good data, or a model that serves as a data generating process. This research stool takes three legs. If one of them's missing, it doesn't stand up. But basically, typically one of them is really strong and the other two may just support the stool. And so a good way to find a research topic, I think, is to start with one of these three legs and then fill out the stool. And I think the Arch paper is sort of in that paradigm that, had a question from Milton Friedman. Inflation data was being modeled in a sort of a time series way, which is interesting. And then the good econometrics ended up being the Arch model. So what happens after the Nobel Prize? Well, after the ceremony, I got a nice kiss from my wife. And even though Alfred Nobel in the background is a little bit unsure what he thinks about this kind of frivolity going on, but then there was more to do. So as you said at the beginning, the press is very pushy. As academics, we're not used to that, or at least I wasn't. And so they ask a lot of questions. They ask questions that you don't know the answer to. They think everybody who gets a Nobel Prize knows the answer to everything. And then they'll say some disarming thing, which I hate, which is, well, you may not be an expert. I just want to know what a smart person thinks about this question. Well, that's really, you can get into a lot of trouble doing that. Anyway, so, and of course they don't want mathematical answers, and that's the way we always talk in the profession with mathematics. So these obstacles can be overcome, but it takes some patience, and actually people can help you with this. Our publicity department was very helpful to me in dealing with this. There's a responsibility to represent the profession, which leads to a lot of things. There is a chance to help humanity with your science, perhaps, and there are overwhelming opportunities. So Nobel Prize winners all end up making a choice as to which of these things they're going to do and which things they're not, because there are too many opportunities. And I think that, well, for me, what was interesting was I was not actually writing about volatility anymore. I was done with that topic. I was on to some other stuff. And when I had to write the Nobel lecture, I realized there were some unanswered questions that really I thought were important. And so I wrote it in part about those questions, and I've actually continued working on volatility because it seems to me even more important and more interesting than when I first did this work. So, financial risk is really part of that. So I've opened an institute at NYU called the Volatility Institute, and it does a lot of things. It has an annual conference. Many of you who have been at this conference, there's a quantitative and financial econometrics seminar that it runs. We've started the Society for Financial Econometrics, or SOFI, which, again, many of you have been involved in SOFI. There are lots of Danish members. Aarhus has been an institutional member for a long time. I've raised money from lots of foundations, and I'm keeping doing that. And if you want to help out, just let me know. And what ties into what I'm going to say next tonight is this website called VLab, or the Volatility Laboratory, which does all sorts of things. It forecasts financial risk on a daily basis for thousands of financial assets. And it measures lots of different kinds of risks. It measures volatility, correlation, systemic risk, long-run value at risk, liquidity, interest rate, and now climate risk. So these are all different sections of the VLab, which are updated on a daily basis from data from all around the world by re-estimating these models. So just to look quickly, in the volatility section, we estimate these models every day. In the correlation models, we estimate these, and in SRISK, we calculate these. So there's a lot of calculation that's going on. And when you put the volatility models together, we put them in a map, so you can kind of see where the volatility is. Volatility is high where it's red and low where it's green. And so one of the things you'll see is that the world is in a low volatility state. I mean, not just the US, but all of Europe pretty much is in a low volatility state. Southeast Asia, China, India, all low volatility. Almost all of Latin America, only Chile. But of course, that's because Chile's having an election next week, and there's a lot at stake in the Chilean election. So the financial markets are red in Chile and in Venezuela. But it doesn't always look like this. This is what it looked like after Brexit. And you see, after Brexit, we had high volatility in all over Europe, US, Canada, to some extent in Latin America and Australia, New Zealand. Interestingly, not in Russia or China or India, Southeast Asia, and so forth. That gradually died away. It's not clear it's gone. It may come back. But then we had another event, which is the US election, and this is a couple days after the election. And what you see is, interestingly, the US still has low volatility even after the election of Trump. The European Union pretty much has low volatility, but we have high volatility in Latin America, in Australia. Now we see it in Indonesia, in the Philippines, Thailand, as well as Japan, Australia, New Zealand. And these are the TPP partners. So we follow these risks around the world with this map. And if you go to the website on your phone right now, you'll see this map that I showed you first. That's the first thing that comes up, is the map. So it's a fun thing to do when you're in a boring lecture or something. So, you know. Okay, so what do we have? We've got these asset classes. This is how many assets I think are in there now, but it keeps changing. These are the countries we study systemic risk for. And what I'd like to do now is show you some of the latest things we're doing to talk about systemic risk. So this is a part of the website, but it's new work that we have just more or less completed. And it's with my PhD student, Tianyu Ruan. So this is a picture of a volcano in Patagonia, where we talk about opportunities. We were there last spring. It's a peaceful scene, but there is a wisp of smoke coming out of this volcano. And so that is sort of the introduction to why we're interested in systemic risk. And let's see if I can get this introduction to play for you here.
The Tungaroa volcano, located in central Ecuador, soars 16,480 feet into the sky. In some ways, the dormant volcano has many similarities to a financial system. It may function calmly for many years, and we may be unaware of its weaknesses. If we take this analogy a step further, volcanologists install measurement devices to see what is going on beneath the surface of the Earth. They use theories of the behavior of the magma to infer the probability of an eruption. Eventually, the dormant volcano may erupt, causing massive damage to the environment and to people's lives. Today, we're going to apply the same methodology to look at the stability of financial markets.
What we want to talk about is systemic risk, but we want to ask a question that normally doesn't get asked, which is how much is really too much? When we say there is systemic risk, do we worry about it? Well, mostly we don't have ways of measuring how much it takes to actually bring on a financial crisis. So here's the questions that I want to ask. When we think about a financial crisis and whether the banking sector is sufficiently well capitalized that it can survive a financial crisis, we do stress tests, and we do them all. Countries all around the world do stress tests, and what that's really asking is, can this bank sustain its operations if there is an external shock, which is something that the central bank creates in its stress test and asks, would this bring down the bank or not? So the normal stress test is based on looking at the response to an external shock. But the reason we do this is because what we're really interested in is the fact that if the banking sector as a whole is not sufficiently well capitalized to survive an external shock, then it will start inexorably its process internally to create the financial crisis. And so undercapitalized banks naturally try to strengthen their balance sheets, and in the process of doing that, they bring on the financial crisis. That's the argument. And if, from that point of view, we can then ask whether the undercapitalization of the financial sector is already sufficient that we're headed for a financial crisis. So what we want to calculate is the probability of a financial crisis depending on the conditions that we see at this point in time. So it's common to think that the result of the financial crisis, the cause of a financial crisis is excessive credit growth. That when credit expands much faster than it should, we are likely to have a financial crisis. But the thing that's hard about this is credit expansion is a natural outcome of growth. And so we can't really be opposed to credit expansion, otherwise we're going to stifle growth. So how do we measure credit expansion that's excessive rather than just good credit expansion? So there are a whole series of papers up here, but this last one, Schulich and Taylor, coins the phrase that a financial crisis is a credit boom gone bust. And the question, of course, we can say with hindsight when that happens, but can we say ahead of time when that happens? So here's a little example which motivates, I think, how we're going to do this measurement. It's a mortgage example, and what we think happens with mortgages is that in the late stages of a credit expansion, where credit may be excessive, banks are going to start making loans to individuals that are not qualified, and on properties that are overvalued. That is, they're not worth as much as the bank thinks they are. As a consequence, the value of this mortgage, the economic value of this mortgage, is less than the accountants think it is. And furthermore, if there is a downturn in the economy or in the housing market, or probably both of them, then you would expect this mortgage to have economic value which falls even further below its accounting value. The bank will probably have to take some of its reserves to make up for this loss in economic value of the mortgage. And if it does not have sufficient reserves to make up this loss, we say the credit growth was excessive. In other words, what we mean by excessive credit growth is that the loans, when they're underwater, require the banks to have a cushion, a financial cushion, which is sufficient to protect the institution against this drop in the value of its assets. And if they don't have sufficient financial cushion, they are going to have to raise capital somehow in the middle of this crisis, and that's what we're going to use to measure this. So the question that I'm going to ask is, how much capital would a financial institution need to raise in order to function normally if we have another financial crisis? So this is an idea of a capital shortfall that is very much like a stress test, but by the way I've developed it, you can see it's also a way of measuring whether there's excessive credit growth going in this financial period. So how do we do this? Well, we think that capital shortfall is a random variable. It depends on this counterfactual that there is a crisis in this economy, and we want to know what the median of this random variable is. We think that for a firm to continue to operate, it should have enough equity so that some fraction of its assets is held in equity. And little k is this fraction. This is a capital ratio. And so little k times the assets, which is debt plus equity, we think should be in reserve. What they actually have in reserve is the true equity. And so if what they need is greater than what they have, there's a capital shortfall. And that's what we want to measure. And the debt in the future is pretty well established by the debt, the face value of the debt that have now. What's different is in a crisis, the equity is going to go down in value. So we need to estimate how much the equity would fall if we have a crisis. And this is done using one of the common tools in finance, which is the beta regression, which regresses the return on the stock market against the return on the market as a whole. That is, take the return from one company and regress it on the market as a whole. And the beta tells you how much of that gets transmitted to this one company. So, for example, if we have a financial crisis and the world equity market goes down by 40%, and your firm has a beta of 1, you would expect your equity value would go down by 40%. And that you can then ask, if your equity goes down by 40%, what's your capital shortfall? But if your beta is 2, it's going to go down by a lot more. And if your beta is 4, it goes down by even more. So depending on what your beta is, it tells you how much risk there is to a certain decline in the global market. So we're going to have to estimate this beta, and that's commonly done by least squares regression or something like that. We're going to do something a little bit fancier just because, well, some of your students, right? Yeah, I want to show you how we do it, really, but only a little bit. That is, we recognize that the beta that you get from a regression coefficient is always the ratio of the standard deviation of the firm over the standard deviation of the market times the correlation between these two. So a regression coefficient always has this simple interpretation. And yet we know that volatilities are continually changing over time. It turns out that correlations are also continually changing over time. So it wouldn't make sense to think of the beta as a constant, except if we're really, really lucky. But normally it's changing over time. And so we want to estimate it with time-varying correlations and time-varying volatilities. So we can do this pretty simply. What we're going to use is a Garch model for, a Garch model of some kind. Here we go. For market returns, an asymmetric Garch model for firm returns, and then a DCC model which talks about how the correlations change over time. And we could put these three things together and say that's what our beta is. But there's a step that I think is useful to do, which is to say, maybe the actual beta really was constant, in which case we are just getting a noisy approximation to it. So if we want to test the hypothesis that beta is equal to a constant, we could think about this as a hypothesis testing problem. However, it's a non-standard one because it's non-nested. And so the way we're going to test this non-standard hypothesis is by using what's called an artificial nesting. That is, create a model which has, as a special case, the constant beta, and as another special case, has the time-varying beta that we've already estimated. And here's what that model really looks like. It's very simple in this case. We now take the return on my company J and regress it on the world stock market return, and this phi would be the constant beta. We also regress it on this time-varying beta that we have up here times the market return, and this coefficient theta tells you whether this term is important. And then actually there's heteroscedasticity left over, which we ought to estimate. So if the beta is really constant, we expect theta would be 0. And if beta is really time-varying, we expect phi to be 0. But what we often find is that they're both significant. So both these terms seem to be important. And this relates to a body of literature that's getting to be very popular now, which are shrinkage estimators. And so what we commonly find is that theta is less than 1, which means that the time-varying beta that we have got here might be a little bit excessive. And once we multiply it by something less than 1, it gives us a much better estimate of what the beta is. And at the same time, we need to add in this constant term phi. So we're going to, in everything I show you, we're going to have phi hat plus theta hat times the time-varying beta as what we're looking at. So this gives us a beta that varies from one day to the next, and it's different for different countries and different companies, and we can compare these things all around the world. Okay, so what do we see when we look at SRISK, which is this measure of capital shortfall for all these different countries? Well, in fact, I'm going to show you some pictures from VLab, but you could go to VLab yourself, and you can even do it with your phone and take a look at this. Or you could become a research affiliate so you can get a computer feed from this. So what do we see when we do this? I'm Rob Engle. I'm a finance professor at NYU and the director of the Volatility Institute. In this short segment, I'm going to show you how to use VLab, which covers the risks of financial markets on a daily basis. When you open the VLab website, this is what you'll find. As you can see, this is a volatility map of the world, where green countries show relatively low volatility and red countries show relatively high volatility. You will see above this map a menu bar with different topics. To see SRISK,
click on the header, Systemic Risk. You will then be taken to a list of the most systemically risky companies in the U.S. From that point, to observe the SRISK on a country basis, click on See More. At this point, you'll see the distribution of SRISK across different countries. At the bottom of the page, there is the total international SRISK. The site can display for either a single country, by region, or across all countries. The site then allows one to normalize by GDP, or by total assets, or by market cap. Another great feature of the VLab site is to be able to see the SRISK and the factors that are used to compute it for all the major financial companies in the world. To see this table, scroll through this menu bar and select Systemic Risk Analysis, and then click Go. The first line indicates the capital shortfall for a country or region. This number is a result of the percentage chosen for global stock market decline over the next 6 months. The default is set to 40%, which is approximately what the global stock market did during the great financial crisis of 2008. Now, scroll down to the bottom of the page and you'll see SRISK evaluated by date, by institution, by capital requirement, and of course by country. The final feature of this section enables you to view changes in SRISK over any time period. In the first column, you'll see SRISK at the first date. In the second column, you'll see SRISK at the second date. And in the third column, you'll see the difference in SRISK between these dates. The remaining columns decompose this change in SRISK through debt, equity, and risk. If you want to learn more about the vast capabilities that VLab offers, then please explore the VLab website today.
Okay, so where is the SRISK? So we're back in Patagonia, actually, and this is a picture of risk. In fact, see that pink visor there? That's my wife. And this is me. This is my son and daughter-in-law. And this guy is the risk manager. And he has about 1.5 seconds left before his career is shortened by putting us all in the drink. So what do we see when we look at VLab for the risk? We see that actually the country with the highest SRISK in the world is China. Next is Japan, France, UK, United States, Germany, Korea, Italy, Canada. But of course, some of these countries are bigger than others. So there's a question how we should normalize this. And this is part of what we're going to do later. You saw that we can normalize it with this website, and we're going to do that in the exercise I'm going to show you next. If we look at the total SRISK over the world, over the last decade, you see the financial crisis was a peak in the total undercapitalization. The amount of capital that would have been needed to recapitalize all the banks in the world was close to $4 trillion. In the European sovereign debt crisis, actually it was even slightly higher according to our estimates, a little above $4 trillion. And then there is a third crisis that doesn't have a name. We don't actually know exactly what this is, but I think we're going to just call this the Chinese financial crisis. Because basically, when China slowed down after its stock market bubble, resource prices fell all over the world, and many banks who had outstanding loans to resource-based companies had rising non-performing loans and falling loan values and falling stock market values, which I think is what we see here. And we're pretty much recovered from that, but we're down to $3 trillion, which is still a lot of money. So where is that? Well, in the US, you see actually a much better story. It's really pretty much been declining effectively over the last decade. And I think the Dodd-Frank Act is probably an important part of why that's happened. If you look in Europe, you see also essentially a decline, but not nearly as rapid as it is in the United States. And I think there's more work to be done in Europe. But if you look in Asia, you see it's really quite the opposite. And this is why we're concerned about China and Japan at the top of this list. This has been increasing in Asia, and if you look at China, you see it's even steeper. So the debt crisis in Japan and China are likely to be important discussions for systemic risk going forward. How about Denmark? Well, Denmark is actually showing a nice decline here. The numbers are smaller because it's a smaller economy, but it's not zero. And what are the companies behind this? Well, the bank that's on the top is Danske Bank. The only other one with a positive SRISK, that means that it would need capital in a financial crisis, is Jyske Bank. These other banks which are in our data set all have negative SRISK, which means that they are overcapitalized or sufficiently capitalized to survive a financial crisis like this. If you look at the detailed information, you see here is the Danske Bank at about $11 billion, Jyske Bank at $2 billion, and all the others are negative. And here we have the decline that you expect. So if the world market goes down by 40%, it looks like Danske Bank would go by 45%. That's based on its beta being bigger than 1. And here's its correlation, volatility, and leverage. These two banks have more leverage than the others, and they have the only positive capital shortfall. So what's happened since the financial crisis? Well, for Danske Bank, the SRISK has dropped from 26 billion to 11. That's a decline of 15 billion. About 5 billion of it has come from reducing its debt, and 9 billion has come from rising equity values in the bank, and there hasn't been much of a change in its risk. So this is how you use this to look at more detail at what's happening, and we have companies all over the world where you can see this. So now the question that I asked before, which is how much S-risk is too much? And it looks like we're there, right? This looks like too much S-risk. It's I don't know whether this is as bad as the boat in Patagonia, but in any case, I'm not going to tell you what happens next in this one. But it did turn out okay. What we'd like to know is what's the probability of being in a crisis, and what is each country's capacity to survive high undercapitalization without having a crisis, without the probability of a crisis being greater than 50%. So the story that makes this model, that's behind this model, is that when firms have high S-risk, they are going to try to improve their balance sheets. And they're going to do it either because their risk managers say you are vulnerable to external shocks, or because the regulators say you must satisfy our capital requirements. It doesn't really matter which source of evidence there is. So how do they go about doing it? Well, one way to do it is to do nothing and hope for good luck, and if you don't get the good luck, you want to bail out. Another thing you might do would be to sell new shares of stock. A third thing you might do would be to sell some of your assets and use the proceeds to retire debt. So these are kind of three strategies that banks can follow in improving their balance sheet, but they have different costs. And that's what we want to look at here. If you're going to hope for the future, then the regulator is going to be very interested in what it's going to cost him relative to GDP. How much of GDP is he going to have to channel to the bank recapitalization? And if that's high, he's going to really push on the banks. Secondly, if the banks are going to sell shares of stock and they have to sell a lot compared to the current market cap, they're going to find that that depresses their stock price dramatically. They're going to not want to do that. So the bigger this number is, the bigger the problem is as well. So both of these, when they're large, suggest a big problem. In the third case, if you're going to sell your assets, who are you going to sell them to? You're going to be selling them to other people who are also trying to sell their assets. If the assets to be sold are a large quantity compared to the quantity of assets that are out there, there's going to be a big price effect on these assets, a big price impact, and it's what we call a fire sale. So that if all the banks in the US feel like they have to sell their mortgage-backed securities because they're undercapitalized, there's no market for them. These banks are at the same time not going to be ready to make new loans to corporations that need it, especially if these corporations are struggling. So this is a credit crunch. This is a financial spiral which leads to a slowdown in GDP and financial crisis at home. So what we want to do now is figure out how important these three effects are and how big they have to be before we're worried about it. So we have to have a dependent variable in this model of how serious is the crisis. And I'm going to use a measure by Romer and Romer, who basically did a painstaking job of looking through old OECD reports to classify for every 6-month period the strength of a financial crisis for each of 24 industrialized countries. They have a number between 0 and 15 for how serious this is, and the first 3 are considered to be minor credit disruptions. When you get to 4 or more, you're talking about big credit disruptions. When you get to 15, it's extremely serious credit disruption. So what I want to do is fit a model to this data using our SRISK over total assets. Let's see, yes. Okay, right. I'm not showing you all the regressions. You're probably going to be okay with that. So the first thing I want to tell you is that this dependent variable is 0 a lot of the time because there's no crisis in these countries a lot of the time. And then it goes up. So the regression line actually isn't a straight line for these countries. It's a hockey stick. And to have a hockey stick as a regression line, you need to use something like a Tobit model. And so this is a Tobit model with fixed effects for each country. And here we did some searching to see what's the best value of these variables. And it turns out the one with total assets is the best regressor to use in this model. And so I've got here total assets and the change in total assets over the last 6 months as the model that I'm going to use to talk about the probability of a crisis and the SRISK capacity. But I also recognize that the rest of the world could have an effect on each country. And so I've put on down here the rest of the world, again divided by total assets, the change in the rest of the world divided by total assets, the rest of the world divided by market value, and the rest of the world's just log SRISK and its change. And so these regressions include that. And so I actually am going to show you 2 sets of results. One is just the country effect, and the second is where the rest of the world where you can see both of these things come in significantly, adds to the explanatory power. So what is it we do? Well, this is the Tobit model, and maybe some of you know it, maybe you don't, maybe you don't care. That's possible, right? Anyway, the Tobit model says that the dependent variable is either 0 or it's a latent variable. That is, it's either 0 or it's positive. And if it's positive, it follows a regression model. But if it's 0, it doesn't. And what we can do from this model is we can ask, what's the probability that y is bigger than any number we have in mind? And then how does that depend on x? So you can calculate this, and with those coefficients that I got, we are going to come up with a probability that we're in a crisis, namely y is bigger than 4. And let's see what we see. So here in the US, the crisis peaked at more than 80% probability of being in a crisis. And we were surely in a crisis, so that's not too shocking. It went up again during the European sovereign debt crisis, but not as much, and now it's become really quite low. If you look at Japan, you can see this thing was not so high. I mean, there was a crisis before our financial crisis. It didn't go up so much here, not so much in Europe either, but today it's really skyrocketing. In the UK, you see the 3 peaks of this quite pronounced. If you look at France, you see that it actually was worse during the European sovereign debt crisis and is somewhat better now. It's actually dropping at the end of the sample period. I think I have Italy here somewhere, don't I? There's Italy. Italy, I just wanted to show you because a lot of you know Italy, and you can see how devastating this second period was, the European sovereign debt crisis. And now it had a third round up here, which is kind of when Monte dei Paschi di Siena was declared bankrupt and taken over. There is a drop, and that's something we hope is permanent, but it's hard to know. That's the advantage of a higher frequency measure like this. And then here's Denmark. So yes, it looked like there was a financial crisis here during 2008. This one was pretty low, and now it's become very low. So what's this capacity thing that I want to look at? I want to know how much SRISK would give us a 50% probability of being in a crisis. Essentially, how much, if our SRISK gets up to this amount, then we are 50% likely to be in a crisis. So I'm going to show you for the country model in red and the global model in green. So plotted on here are 3 curves. The blue one for the US is our SRISK, and this is the same as what you see on the website, although it's essentially the same. The red one shows, interestingly, that the capacity of the US economy to absorb undercapitalization has grown over time, and that's because the total assets in the banking sector has grown over time. And it's, here we peaked above the 50% point, touched on it here, but as the capacity goes up and the SRISK comes down, the probability of a crisis gets lower and lower. But interestingly, when you look at the green one, you see that what happened during the financial crisis is that the capacity came down just as much as our SRISK went up. And the reason for that is because the rest of the world was weaker. When the rest of the world is undercapitalized, it makes a financial crisis more likely in the US. And that is part of the externality that we talk about in economics. There's an externality between this country and the rest of the world. now, as well as between firms within this country. So let me just, I'm just about out of time, let me just bang through these other pictures. Here you see Japan, and you can see that the rise of SRISK has continued to go up, and the capacity has pretty much gone up with it. If you look at the UK, you see the big decline in capacity during the financial crisis, a smaller decline during the European sovereign debt crisis, and then a little bit in here. Here's Italy, and you see that SRISK is really way above its capacity during the European sovereign debt crisis. They were really in big trouble there. And finally, here's Denmark, and you see the capacity is high relative to the level of SRISK in the Danish banking system. So let me conclude with the last picture, which is two of my grandsons looking out over a lake. It's very calm, just like the volcano. It's very calm, but will it stay that way? What's in their future is one of the reasons why we study financial crises, because we want to make sure we don't do this again. And I think that's a lesson that's important for us to keep in mind. And I would say it's especially important in the US, because we're in the process of dismantling this apparatus because it's worked for 10 years. And I don't really think that's very good long-run view. So let me stop here. Thank you.